On July 12, 2025, astronomers detected something extraordinary. An object moving at over 290,000 kilometers per hour, racing through our solar system on a path that originated from beyond our sun's influence. This wasn't a comet we'd seen before. This wasn't an asteroid caught in our solar neighborhood. This was something from another star system entirely, 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system. And immediately, questions arose: where did it come from? What is it made of? And the question that spread across social media faster than the object itself was traveling through space. Could it impact Earth? I'm here to answer that question, not with speculation, not with sensationalism, but with science, data, and evidence. This is a deep dive into what we actually know about 3I Atlas, what the analysis really shows, and what this remarkable visitor tells us about our place in a universe far more dynamic than we ever imagined. Let's begin with the discovery itself. The story of 3I Atlas begins with a network of telescopes scanning the night sky every single night. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, consists of 4 telescopes strategically positioned across the Earth. Their mission is straightforward but monumental: scan the entire visible sky every 24 hours, looking for anything that moves. On that night in July, the Atlas system in South Africa captured something unusual, a faint point of light that hadn't been there in previous scans. Within hours, astronomers began the careful work of determining exactly what they were looking at. The first step was to calculate its orbit. This isn't as simple as taking a single photograph. Astronomers need multiple observations spread over time to determine how an object is moving through space. Where is it now? Where was it an hour ago, 6 hours ago, a day ago? From these data points, they can work backward and forward to trace the complete path of the object. By July 15th, just 3 days after the initial detection, something remarkable became clear in the calculations. The orbit wasn't elliptical, it was hyperbolic. And that single fact changed everything. Teams around the world immediately began coordinating observations. The European Southern Observatory in Chile, the Subaru Telescope in Hawaii, the Pan-STARRS survey. Within a week, dozens of telescopes across the planet were tracking this object, gathering every piece of data they could before it disappeared back into the darkness of interstellar space. The international astronomical community mobilized with the kind of urgency usually reserved for potentially hazardous asteroids. But this wasn't about planetary defense. This was about capturing data from a visitor that might not come around again for millions of years, if ever. Because unlike the asteroids and comets that belong to our solar system, 3I Atlas was just passing through. To understand why astronomers were so certain that 3I Atlas came from beyond our solar system, we need to talk about orbital mechanics. Every object in space moves according to the same fundamental laws that Isaac Newton described over 3 centuries ago. When an object orbits the Sun, its path is determined by 2 things: the Sun's gravitational pull and the object's velocity. If you've ever swung a ball on a string in a circle, you understand the basic principle. The string pulls the ball inward, while the ball's motion tries to carry it outward. The balance between these forces determines the shape of the path. For objects bound to our solar system, that path is an ellipse. It might be a nearly circular ellipse, like Earth's orbit. It might be a highly elongated ellipse, like some comets that swing close to the Sun and then travel far beyond Neptune before returning thousands of years later. But it's still an ellipse. These objects are gravitationally bound to the Sun. They belong here. But there's a critical threshold. If an object is moving fast enough, the Sun's gravity cannot hold it. The path becomes a hyperbola, a curve that comes in from infinity, swings around the Sun, and departs back to infinity. The object is not bound, it's merely passing through. This threshold is called escape velocity, and for our solar system, it varies depending on how far you are from the Sun. Near Earth's orbit, escape velocity is about 42 kilometers per second. An object moving faster than that cannot be captured by the Sun's gravity. When astronomers calculated 3I Atlas's orbit, they found it was traveling at approximately 81 kilometers per second relative to the Sun, nearly twice escape velocity. The mathematics were unambiguous. This object originated from interstellar space, and it would return to interstellar space. Our solar system was merely a brief waypoint on a journey that began long ago and would continue long after the object left our neighborhood. But determining that an object is interstellar is just the beginning. The next question is, what exactly are we looking at? The challenge here is significant. 3i Atlas is extraordinarily faint. Even through the most powerful telescopes on Earth, it appears as nothing more than a dim point of light. We cannot see its surface, we cannot make out its shape. Everything we know about this object must be deduced from the tiny amount of light it reflects toward Earth. Historically, these discoveries have been vanishingly rare because interstellar objects are incredibly difficult to detect. They're traveling fast, they're usually small, and they don't stay in the inner solar system for long. For modern automated sky surveys, like Atlas and Pan-STARRS, we simply didn't have the capability to scan enough of the sky frequently enough to catch these fleeting visitors. The first confirmed interstellar object, 1i Oumuamua, wasn't discovered until October 2017. The second, 2i Borisov, was found in August 2019. Now, in 2025, we have our third. And each discovery tells us that these visitors are likely far more common than we once thought. We're simply getting better at seeing them. So what do we know about 3i Atlas itself? Let's examine the evidence. First, size. Estimating the size of a distant, faint object is challenging because what we measure is not the object itself, but the amount of sunlight it reflects. This depends on both its size and its reflectivity, or albedo. A small, bright object can reflect the same amount of light as a large, dark object. Based on its brightness and making reasonable assumptions about its albedo, astronomers estimate that 3i Atlas is somewhere between 200 and 400 meters in diameter. That's roughly the length of 3 to 6 football fields. Significantly smaller than 2i Borisov, which was estimated at about 1 kilometer across, but potentially larger than some estimates for 1i Oumuamua. The uncertainty here is important to acknowledge. We're not measuring the object directly. We're inferring its properties from limited data. This is a reminder that astronomy often requires working with incomplete information and embracing the uncertainty that comes with it. Next, spectroscopy. When sunlight reflects off an object, that light carries information about what the object is made of. Different materials absorb and reflect different wavelengths of light. By spreading the reflected light into a spectrum and analyzing which wavelengths are present or absent, we can determine the chemical composition of the surface. Initial spectroscopic observations of 3i Atlas show a spectrum consistent with a mixture of rock and ice, similar to comets in our own solar system. There are absorption features suggesting the presence of water ice, possibly carbon dioxide ice, and silicate minerals. This is not surprising. Comets form in the cold outer regions of planetary systems, and we would expect interstellar objects to have similar origins in other star systems. However, and this is crucial, we're still gathering data. The spectroscopic observations require the object to be bright enough and positioned favorably for detailed study. As 3i Atlas moves through our solar system, different telescopes have different opportunities to observe it. Each new observation adds to our understanding. One particularly interesting characteristic is the object's brightness variation. As it rotates, the amount of light we see from it changes slightly. This tells us that the object is not perfectly spherical. It's elongated or regularly shaped, tumbling through space as it travels. The rotation period appears to be approximately 7.3 hours, though this too comes with uncertainty. Comparing 3i Atlas to its interstellar predecessors reveals both similarities and differences. Like 2i Borisov, 3i Atlas appears to be actively outgassing as it approaches the Sun, producing a faint coma of gas and dust. This behavior is typical for comets. Unlike 1i Oumuamua, which famously show unusual acceleration that spark considerable debate, 3i Atlas seems to be following a predictable trajectory consistent with a comet releasing gas as it warms. The differences are as scientifically valuable as the similarities. Each interstellar object is a sample from a different planetary system, potentially formed under different conditions, around a different type of star. The fact that they are not all identical tells us something profound about the diversity of planetary formation across the galaxy. But all of this analysis depends on one critical factor: the object's trajectory. Where is it going? How close will it come to Earth? And this brings us to the question that brought many of you to this video in the first place. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. To understand whether 3I Atlas poses any threat to Earth, we need to understand how objects move through space and how astronomers calculate their trajectories. This requires diving into orbital mechanics, the physics that governs everything from satellites around Earth to galaxies orbiting each other. The foundation is Newton's law of universal gravitation. Every object with mass attracts every other object with mass. The strength of that attraction depends on two things: how massive the objects are, and how far apart they are. The force increases with mass and decreases with the square of the distance. In our solar system, the Sun's mass dominates. It's 99.86% of all the mass in the entire solar system. Everything else, all the planets, asteroids, comets, dust, and gas combined, makes up less than 0.2%. This means that for most purposes, calculating an object's path through the solar system means calculating how it moves in the Sun's gravitational field. But most purposes isn't good enough for precision work. If you want to know exactly where an object will be weeks or months from now, you need to account for the gravitational influences of the planets as well. Jupiter, with its massive bulk, can noticeably alter the trajectory of objects that pass near it. Even smaller bodies, like Earth, can have measurable effects if an object comes close enough. This is where the mathematics becomes complex. Calculating the motion of two bodies, say, Earth orbiting the Sun, can be done with elegant equations that have exact solutions. But add a third body, and suddenly, there are no exact solutions. The three-body problem, as it's known, requires numerical methods. Computers simulate the motion step by step, calculating the forces at each moment and updating the positions and velocities accordingly. For 3I Atlas, astronomers use sophisticated software that tracks not just the Sun and planets, but also accounts for other effects. Solar radiation pressure, for example. Photons from the Sun carry momentum, and when they strike an object, they exert a tiny push. For small objects like asteroids and comets, this pressure is measurable. For a comet that's outgassing, the effect is even more pronounced because the escaping gas creates a rocket-like thrust. Every observation of 3I Atlas provides data that astronomers feed into these models. Where was the object at this precise time? How bright was it? From these observations, they refine the calculated orbit, reducing the uncertainty with each new data point. When astronomers publish orbital elements for an object like 3I Atlas, they're not just giving a single trajectory. They're providing a solution with error bars. The most likely path, along with a range of possible paths that fit the observations within the measurement uncertainties. As more data comes in, that range narrows, the trajectory becomes more certain. For 3I Atlas, after weeks of observations from multiple telescopes around the world, the trajectory is now known with high confidence. And this is where we can directly address the impact question. Let's talk about the actual numbers, hard data, not speculation. As of the latest orbital calculations, 3I Atlas's closest approach to Earth will occur in mid-October 2025. At that point, the object will be approximately 273 million kilometers from Earth. That's 273 million kilometers. To put that in perspective, that's 1.82 astronomical units. 10 is the average distance between Earth and the Sun, roughly 150 million kilometers. So 3I Atlas will pass Earth at nearly twice the Earth-Sun distance. The Moon orbits Earth at an average distance of 384,000 kilometers. 3I Atlas will pass more than 700 times farther away than the Moon. If you represented Earth as a basketball and the Moon as a tennis ball about 7 meters away, 3I Atlas would be passing nearly 5 kilometers away. Some earlier reports mentioned a distance of 170 million miles. Let me clarify that number. That figure referred to the minimum distance at a different point in the object's trajectory through the solar system, not specifically its closest approach to Earth. In space, distances can be measured in several ways: distance from Earth, distance from the Sun, distance from the plane of the solar system. It's crucial to specify exactly what distance we're talking about. What's unambiguous is this: there is zero possibility of impact with Earth. Zero. The uncertainty in the trajectory is far, far smaller than the actual distance of closest approach. Even accounting for all possible sources of error in the measurements and calculations, there is no scenario in which 3I Atlas comes anywhere near Earth. Now let's talk about velocity. 3I Atlas is traveling at approximately 81 kilometers per second relative to the Sun. That's 291,600 kilometers per hour. At this speed, the object could travel from New York to Los Angeles in less than 2 seconds. This extraordinary velocity is part of what makes interstellar objects so challenging to study. They're here, and then they're gone. 3I Atlas will spend only a few months in the inner solar system before heading back out into the darkness beyond the orbit of Neptune, never to return. For comparison, Earth orbits the Sun at about 30 kilometers per second. The fastest human-made object, the Parker Solar Probe, has reached speeds of about 163 kilometers per second relative to the Sun. 3I Atlas is traveling at half that spacecraft's maximum velocity, but it's doing so without any propulsion, carried purely by the momentum it gained wherever it originated in the galaxy. The object's trajectory has been calculated forward and backward in time. Working backward, astronomers can trace roughly where 3I Atlas came from, though the uncertainty grows the further back you go. The current best estimate suggests it originated from the general direction of the constellation Gemini, though pinpointing a specific star of origin is essentially impossible. The object has been traveling through interstellar space for potentially millions of years. Working forward, the trajectory shows that after passing through the inner solar system, 3I Atlas will head back out, eventually crossing the orbit of Neptune in 2026 and continuing into the Kuiper belt and beyond. By 2030, it will be beyond the orbit of Pluto. By 2040, it will be in the distant region where the Sun's gravitational influence begins to fade into the background of the galaxy. These are not estimates. These are not approximations. These are calculations based on the fundamental physics that governs every object in the universe, backed by hundreds of precision observations from professional observatories around the world. Even before the precise trajectory was calculated, astronomers knew that an impact was extraordinarily unlikely. Understanding why requires appreciating just how vast and empty space actually is. Consider the volume of space within Earth's orbit around the Sun. If you imagine a sphere with a radius equal to Earth's orbital distance, the volume of that sphere is approximately 1.4 billion cubic astronomical units. That's a number so large it's difficult to grasp. Now consider Earth itself. Our entire planet has a cross-sectional area of about 127 million square kilometers. That sounds like a lot. But when you're talking about the volume of space within the orbit, Earth represents an unimaginably tiny target. Let me give you an analogy. If you scaled the solar system down so that the Sun was the size of a basketball, Earth would be smaller than a grain of sand, and that grain of sand would be orbiting 26 meters away. An object like 3I Atlas would be a speck of dust traveling through this system. The probability of that speck of dust randomly hitting that specific grain of sand is essentially zero. The history of the solar system bears this out. Over the past 4.5 billion years, countless objects have passed through the inner solar system. Most missed everything. Some impacted planets or moons, and we can see the craters they left behind. But the overwhelming majority simply traveled through empty space, perturbed slightly by the planet's gravity, and continued on their way. When astronomers detect a new object, whether it's an asteroid, comet, or interstellar visitor, they immediately begin calculating its trajectory for one specific reason: to determine if there is any possibility of Earth impact. This is the job of NASA's Center for Near-Earth Object Studies and similar organizations around the world. They use two scales to assess impact risk: the Torino scale and the Palermo Technical Impact Hazard Scale. The Torino scale is a simple, color-coded system designed for public communication. It ranges from 0 to 10. 0 means no hazard or the object will definitely miss Earth. 1 through 10 indicate increasing levels of concern. A level 10 represents a certain collision capable of causing a global catastrophe. In the entire history of the Torino scale, no object has ever been rated higher than 4, and those ratings were subsequently downgraded to 0 as better data refined the trajectories. The Palermo scale is more technical. It compares the probability of a specific impact to the background risk of an impact from a random object of the same size. A value less than -2 means the object is of no practical concern. 3i Atlas scores a 0 on the Torino scale. Its Palermo scale value isn't even calculated because the impact probability is exactly 0. There is no ambiguity here, no small chance, no might miss, it will miss. The trajectory doesn't come close to intersecting Earth's orbit. Some of you might have seen alarming posts on social media suggesting otherwise. Let me address where that misinformation came from. In the early days after 3i Atlas's discovery, before sufficient observations had been made to precisely calculate the orbit, there was uncertainty. This is normal and expected, but some individuals misunderstood or deliberately misrepresented that uncertainty, suggesting that an impact was possible. What they failed to understand or chose to ignore is that even large uncertainty in an orbit doesn't automatically mean impact is possible. The initial observations still constrain the trajectory to a broad region of space, and even within that uncertainty, Earth was not in the range of possibilities. Additionally, some confusion arose from the fact that NASA does use objects like 3i Atlas in training exercises for planetary defense. But being used in an exercise doesn't mean the object is actually a threat. It means the object provides a useful scenario for teams to practice coordination, communication, and analysis procedures. The exercise is about improving our response capabilities for when a real threat does eventually appear, not because 3i Atlas itself is dangerous. The scientific community has been clear and consistent from the beginning. 3i Atlas poses no threat to Earth. The social media panic was based on misunderstanding, not evidence. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. This seems like an appropriate moment to talk about how humanity actually monitors and responds to potential impact threats, because 3i Atlas exists within that larger context. NASA's Planetary Defense Coordination Office, or PDCO, was formally established in 2016, though the work of tracking near-Earth objects began decades earlier. Its mission is straightforward: detect, track, and characterize potentially hazardous asteroids and comets, and coordinate a response should a real threat be identified. The office works closely with a network of ground-based telescopes and space-based observatories. The surveys I mentioned earlier, ATLAS, Pan-STARRS, the Catalina Sky Survey, are all part of this effort. Every night, these telescopes scan the sky, looking for moving objects. When something new is found, it's reported to the Minor Planet Center at the Harvard-Smithsonian Center for Astrophysics, where the data is collected, verified, and distributed to astronomers worldwide. As of today, astronomers have catalogued over 35,000 near-Earth objects. These are asteroids and comets whose orbits bring them within 1.3 astronomical units of the Sun, which means they can potentially come close to Earth. Of these, about 2,300 are classified as potentially hazardous objects, or PHOs. These are objects larger than 140 meters in diameter that can come within 0.05 astronomical units of Earth's orbit, about 7.5 million kilometers. Being classified as potentially hazardous doesn't mean these objects are going to hit Earth. It means they're large enough to cause significant damage if they did, and their orbits bring them close enough that we need to keep watching them. The vast majority of PHOs have well understood orbits, and we know with certainty that they pose no threat for at least the next century. The PDCO's work isn't just about detection. It's also about developing response capabilities. If we did identify an asteroid on a collision course with Earth, what would we do about it? This is where the DART mission becomes relevant. The Double Asteroid Redirection Test, launched in 2021 and executed in September 2022, was humanity's first test of planetary defense technology. The spacecraft deliberately crashed into Dimorphos, a small moon orbiting the asteroid Didymos, to see if the impact would change the moon's orbit. It worked. The impact altered Dimorphos's orbital period by 33 minutes, far more than the minimum 73 seconds needed to declare the mission a success. This demonstrated that kinetic impact, simply crashing something into an asteroid at high speed, is a viable method for deflecting a threatening object, provided we have enough warning time. The key phrase there is enough warning time. Deflecting an asteroid isn't like a science fiction movie where heroes save the day at the last minute. It requires years, possibly decades of advance notice. A small nudge delivered years before a predicted impact can shift an asteroid's trajectory by enough to make it miss Earth entirely. But that same nudge delivered only months before impact would be useless. This is why the detection and tracking work is so critical. The earlier we know about a potential threat, the more options we have for dealing with it. And this is why organizations like the PDCO exist, to ensure that we do have that warning. Now, let's return to 3i Atlas and address why it's been used as a training scenario, because this has been a source of some confusion and anxiety. Every few years, the international planetary defense community conducts exercises to test and improve their coordination and response capabilities. These exercises typically involve a hypothetical asteroid impact scenario. Teams from different countries and organizations work through the scenario, practicing how they would detect, track, analyze, and ultimately respond to a real threat. 3i Atlas provides an interesting real-world scenario for such an exercise, not because it's actually threatening, but precisely because it isn't. It allows teams to practice their procedures: data collection, trajectory calculation, risk assessment, public communication using a real object with all the messiness and uncertainty that comes with real data, but without the pressure and panic that would accompany an actual threat. Think of it like a fire drill. The building isn't actually on fire, but practicing the evacuation procedures when there's no real danger means people will respond more effectively if there ever is a real fire. Similarly, using 3i Atlas as an exercise scenario means that if we ever do detect a real impact threat, the teams involved will have practiced their coordination and communication, and they'll respond more effectively. These exercises involve multiple components. First, there's the technical analysis, calculating orbits, assessing impact probabilities, evaluating potential deflection strategies. Second, there's the coordination, ensuring that information flows properly between different agencies and international partners. Third, there's the communication, determining how to inform the public, media, and decision-makers in a way that's accurate, timely, and doesn't cause unnecessary panic. That last component is particularly challenging. How do you communicate uncertainty? In the early days after a new object is discovered, there's always uncertainty in the orbit calculation. That uncertainty typically decreases rapidly as more observations are made. But in that early period, if there's even a tiny probability of impact, do you inform the public? Do you wait until more data comes in? How do you explain the situation without either causing panic or appearing to hide information? 3i Atlas provided a real-world scenario for practicing exactly these communication challenges. Early on, before the trajectory was precisely known, it offered an opportunity to practice how you'd communicate about an object with uncertain trajectory. Then, as more data came in and the trajectory became clear, it offered an opportunity to practice communicating that the object definitely poses no threat. The fact that NASA used 3i Atlas in an exercise doesn't mean NASA was worried about it. It means NASA is being responsible about preparing for future scenarios when we might have something to actually worrying about. It's also worth noting that the international nature of these exercises is crucial. Asteroids don't respect national borders. If a threatening object were ever detected, the response would need to be coordinated internationally. These exercises help build the relationships and communication channels that would be essential in a real scenario. So if 3i Atlas isn't a threat, what are the real threats? What objects are astronomers actually concerned about? Let's start with what's on the watch list. NASA and international partners maintain a continuously updated list of objects that require ongoing monitoring. These aren't objects that are going to hit Earth, but objects where the impact probability, while extremely small, is not precisely zero. The most famous example in recent years is Apophis. This asteroid, about 370 meters in diameter, was discovered in 2004. Initial observations suggested a small but real probability of impact in 2029. This probability was high enough that Apophis briefly reached level 4 on the Torino scale, the highest any object has ever reached. However, additional observations refined the orbit calculation, and by 2021, astronomers could conclusively rule out any impact risk from Apophis for at least the next 100 years. Apophis will still make a very close approach to Earth on April 13, 2029, It will pass within 31,000 kilometers of Earth's surface closer than some satellites. This will be an extraordinary opportunity for science. Telescopes and radar systems around the world will study the asteroid in unprecedented detail. But it will not impact Earth. Another object that's received significant attention is Bennu. This asteroid is about 500 meters in diameter, and it's the target of NASA's OSIRIS-REx mission, which collected a sample from the asteroid's surface in 2020 and returned it to Earth in 2023. Bennu has a small probability of impacting Earth late in the 22nd century specifically. There's about a 1 in 2,700 chance of impact between 2175 and 2199. This might sound alarming, but let's put it in perspective. First, that's over 150 years from now. Second, a 1 in 2,700 chance means a 99.96% chance that it won't hit Earth. Third, over the next several decades, continued observations will refine Bennu's orbit further, and that probability will likely drop to zero, just as it did for Apophis. And fourth, even if Bennu were on a collision course, we have 150 years to prepare a deflection mission. The real concern isn't the objects we know about. It's the ones we haven't discovered yet. Current surveys have found approximately 95% of near-Earth objects larger than 1 kilometer in diameter. But for smaller objects, say, 140 meters in diameter, we've only cataloged about 40% of them. These smaller objects wouldn't cause a global catastrophe if they impacted, but they could still devastate a city. This is why the work of surveys like Atlas and Pan-STARRS continues. Every night, they scan the sky, looking for objects we haven't seen before. And every new discovery is another object we can track, characterize, and eliminate as a potential threat or identify as something that requires further attention. Now, here's an interesting point about interstellar objects specifically. Objects like 3 Atlas are actually less concerning from a planetary defense standpoint than near-Earth asteroids. Why? Because interstellar objects are just passing through. They're not in orbit around the Sun. They come in from interstellar space, swing through the solar system once, and leave. They don't come back. Near-Earth asteroids, on the other hand, orbit the Sun just like Earth does. Their orbits can evolve over time due to gravitational perturbations. An asteroid that poses no threat today might, over thousands or millions of years, end up on an orbit that crosses Earth's, or an orbit that's currently safe might, due to a close encounter with another planet, be altered into a threatening one. With interstellar objects, there's no long-term evolution to worry about. Either they're on a collision course when we first detect them, or they're not. And given the vastness of space and the speed at which they're traveling, the probability of any random interstellar object being on a collision course is vanishingly small. In fact, in the entire history of Earth, it's quite possible that no interstellar object has ever impacted our planet. The number of impacts we've had from solar system objects, asteroids, and comets far outnumbers any potential contribution from interstellar visitors. The dinosaur-killing impact 66 million years ago was almost certainly a solar system asteroid or comet, not an interstellar object. So while 3 Atlas is scientifically fascinating, it's not something that keeps planetary defense experts awake at night. What does keep them focused is the ongoing work of cataloging the solar system's native population of near-Earth objects and ensuring we have the technology and plans in place to respond if we ever do identify a real threat. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. To fully appreciate 3 Atlas and what it represents, we need to understand its 2 interstellar predecessors. And that means we need to talk about Oumuamua. On October 19, 2017, astronomer Robert Warwick was reviewing images from the Pan-STARRS telescope in Hawaii when he noticed something unusual. A faint, fast-moving object that didn't match any known asteroid or comet. Within days, as astronomers around the world turned their telescopes toward it, the realization dawned. This object had come from beyond our solar system. They named it Oumuamua, a Hawaiian word roughly meaning scout or messenger from the distant past. The name was fitting. This was the first confirmed interstellar object ever detected, and it would prove to be far more mysterious than anyone anticipated. Oumuamua's trajectory was unambiguously hyperbolic. It had entered the solar system from the direction of the constellation Lyra, swung past the Sun at high speed, and was heading back out toward the constellation Pegasus. By the time astronomers detected it, it had already passed its closest approach to the Sun and was on its way out. This meant there was only a limited window to study it before it became too faint and distant to observe. And that's where the controversy began. Because the more data astronomers collected, the stranger Oumuamua appeared. First, there was the shape. Based on how its brightness varied as it rotated, astronomers calculated that Oumuamua was highly elongated, potentially 10 times longer than it was wide. Some estimates suggested it might be shaped like a cigar, about 400 meters long and only 40 meters wide. Later analyses proposed it might be flatter, more like a pancake. Either way, it was unusually shaped for a natural object. Second, there was the lack of a coma. When comets approach the Sun and warm up, ice on their surface sublimates, turns directly from solid to gas, creating a visible coma of gas and dust. But Oumuamua showed no evidence of a coma, at least not one detectable with the available observations. This suggested it might not be a typical icy comet. Third, and most controversially, there was its acceleration. In June 2018, 8 months after the discovery, a team of astronomers published a paper showing that Oumuamua's trajectory didn't quite match what would be expected from gravity and solar radiation pressure alone. The object was accelerating, as if something were giving it an extra push. For a comet, this wouldn't be unusual. The outgassing of ice creates a rocket-like thrust. But remember, Oumuamua hadn't shown clear evidence of a coma, so what was causing the acceleration? This is where things got interesting. A few scientists, most prominently Harvard astronomer Avi Loeb, suggested that Oumuamua might not be a natural object at all. Perhaps it was a light sail, a thin reflective sheet pushed by some light, possibly artificial in origin, perhaps even an alien probe. The media, predictably, seized on this idea. Headlines proclaimed Harvard astronomer says object might be alien spacecraft. The public fascination was intense. Here, finally, was potential evidence of extraterrestrial intelligence visiting our solar system. The scientific community's response was more measured. Most astronomers found the artificial hypothesis necessary. There were natural explanations that, while requiring some special conditions, were far more plausible than invoking alien technology. One hypothesis suggested that Oumuamua might be a hydrogen iceberg. Hydrogen ice sublimates at very low temperatures, producing a nearly invisible outgassing that could explain the acceleration without producing a visible coma. Another idea proposed that the object might be made primarily of nitrogen ice, similar to the surface of Pluto. Nitrogen ice would also sublimate without producing the typical coma we associate with water ice comets. A more recent hypothesis suggests Oumuamua might be what's called a dust bunny, a loosely bound aggregate of dust and ice with a very low density. Such an object would have a large surface area relative to its mass, making it more susceptible to radiation pressure and outgassing effects. The challenge in evaluating these hypotheses is that by the time scientists realized how unusual Oumuamua was, it was already too faint and distant to study in detail. We'll never get better data on Oumuamua itself. All we have are the observations made during that brief window in late 2017 and early 2018. So what are we to make of the controversy? The honest answer is that we don't know exactly what Oumuamua was. The available evidence rules out many possibilities, but it doesn't definitively confirm any single explanation. What we can say is this: invoking an artificial origin is scientifically unwarranted. Extraordinary claims require extraordinary evidence, and the evidence for Oumuamua being artificial is not extraordinary. It's consistent with natural processes, even if those processes are unusual or not fully understood. The scientific value of Oumuamua isn't in proving aliens exist. It's in showing us that our understanding of interstellar objects, based on zero detected examples before 2017, was incomplete. Nature surprised us, and science is at its best when it's being surprised. The public reaction to Oumuamua also taught the scientific community valuable lessons about science communication. When dealing with unusual observations, how do you convey the genuine scientific uncertainty without fueling unfounded speculation? How do you acknowledge that something is strange without declaring it to be alien? These are questions that became relevant again when the second interstellar object was discovered. On August 30, 2019, amateur astronomer Gennady Borisov was conducting his regular survey of the night sky from the Margot Observatory, in Crimea, when he spotted a new comet. Within a few days, as professional observatories confirmed the object and calculated its trajectory, it became clear this was the second interstellar object ever detected. They named it to Borisov, following the designation system where the number indicates the order of discovery and the name honors the discoverer. And this time, the scientific community was ready. Unlike Oumuamua, which was discovered after it had already passed the Sun and was heading outward, Borisov was detected while still approaching the inner solar system. This meant astronomers had months to observe it, plan their observations, and coordinate efforts across multiple telescopes and observatories. What they found was, in many ways, reassuring. Borisov looked and behaved like a comet. It had a clear coma and tail. It was outgassing water vapor, carbon monoxide, and other volatiles as it warmed. Its spectrum showed features consistent with dust and ice. In short, it was exactly what you'd expect an interstellar comet to look like. Spectroscopic analysis revealed that Borisov's composition was remarkably similar to comets in our own solar system. This was scientifically significant. It suggested that the processes of planet and comet formation might be similar across different star systems. The building blocks that form comets around our Sun might be the same building blocks that form comets around other stars. There were some differences, of course. Borisov appeared to have higher than typical concentrations of carbon monoxide relative to water. It was also unusually rich in certain types of dust particles. But these differences were minor variations, not fundamental departures from what we see in solar system comets. The shape of Borisov was less unusual than Oumuamua. It appeared to be roughly spherical or only moderately elongated, nothing like the extreme cigar or pancake shape proposed for Oumuamua. And critically, Borisov's trajectory was entirely consistent with gravitational forces and outgassing effects. There was no mysterious acceleration that needed explaining. It followed the path we expected it to follow. In a sense, Borisov was the normal interstellar object. It was what many astronomers had expected the first interstellar visitor to look like. The fact that Oumuamua had been so unusual now appeared to be a fluke, a reminder that the first example of something is not necessarily representative of the entire population. The scientific return from Borisov was substantial. Over a dozen major research papers were published analyzing different aspects of the object. We learned about its composition, its nucleus size estimated at about 1 kilometer, its rotation period roughly 8 hours, and its gas and dust production rates. Perhaps most importantly, Borisov gave us confidence in our ability to detect and study interstellar objects. When the next one appeared, we'd know what to do. We'd have protocols in place, we'd have observing programs ready to deploy. We'd have comparative data from previous interstellar visitors to help interpret what we were seeing. Which brings us to 2025, and the third detection. 3 Atlas shares characteristics with both of its predecessors, while also showing some features that make it scientifically intriguing in its own right. Like Borisov, 3 Atlas appears to be a typical comet. It's outgassing, it has a coma. Its trajectory is consistent with gravitational forces and the rocket effect from outgassing. There's no mysterious acceleration like Oumuamua showed. Like Oumuamua, 3 Atlas was detected after it had already passed its perihelion, its closest approach to the Sun. This means we missed the period when it would have been brightest and most active. However, unlike Oumuamua, 3 Atlas was detected early enough that there's still a substantial observing window before it becomes too faint. What makes 3 Atlas particularly interesting scientifically is that it's giving us a third data point in our understanding of interstellar objects. In statistics, 3 data points allow you to start identifying patterns and trends. With only 2 examples, you can't distinguish between a pattern and a coincidence. So what are we learning? First, that interstellar comets might be more common than interstellar asteroids, or at least more easily detectable. All 3 confirmed interstellar objects have shown cometary characteristics, though to varying degrees. This could be a selection effect. Comets are easier to detect because they brighten as they outgas, but it's also possible that comets are simply more common than rocky asteroids among interstellar objects. Second, we're learning about the diversity of these objects. Oumuamua was highly unusual, Borisov was typical. 3A Atlas falls somewhere in between, showing some unusual features in its spectroscopic data that astronomers are still analyzing. Early spectroscopic observations of 3A Atlas have revealed some interesting chemical signatures. There appears to be a higher than typical abundance of certain carbon-bearing molecules in the coma. Whether this represents a genuinely unusual composition or simply the specific chemistry of the region where 3A Atlas formed is still being investigated. The observational campaign for 3A Atlas is ongoing. Multiple space-based telescopes, including the Hubble Space Telescope, have been granted time to observe the object. Ground-based observatories across the world are tracking it. Radio telescopes are attempting to detect specific molecular emission lines from the coma. One particularly exciting aspect of studying 3A Atlas is that we can compare it directly to both Oumuamua and Borisov using similar observational techniques. This allows for controlled comparisons that wouldn't be possible if we were studying them with completely different instruments and methods. There are questions about 3A Atlas that we may never be able to answer. Where exactly did it originate? Was it ejected from a planetary system, or has it been wandering the galaxy for millions of years since the molecular cloud it formed and dissipated? How typical is it of objects in interstellar space? These uncertainties are a reminder of the fundamental challenge in studying interstellar objects. We get one chance. These objects pass through our solar system once and never return. We can't send a spacecraft to study them up close, at least not with current technology. We're limited to whatever observations we can make during the brief period they're close enough and bright enough to detect. But even with these limitations, every interstellar object teaches us something. They're samples from other parts of the galaxy, delivered to us free of charge. Each one is a gift to science, a chance to learn about planetary systems beyond our own in ways that wouldn't otherwise be possible. As 3A Atlas continues its journey through our solar system over the coming months, astronomers will continue their observations, gathering every possible piece of data before the object fades into the darkness from which it came. The results will be published in peer-reviewed journals, adding to our growing understanding of these mysterious visitors. And someday, perhaps soon, there will be a fourth interstellar object detected, and a fifth. And eventually, we'll have enough examples to truly understand these cosmic wanderers and the stories they tell about the galaxy we inhabit. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. With 3 confirmed interstellar objects detected in the span of 8 years, a natural question arises: how many of these objects are actually passing through our solar system, and why are we only seeing them now? To answer this, we need to think about both the actual abundance of interstellar objects and our ability to detect them. Let's start with detection capabilities. Before the development of modern automated sky surveys in the 2000s and 2010s, we simply didn't have the tools to detect most interstellar objects. Traditional astronomy involved telescopes looking at specific target stars, galaxies, nebulae, gathering detailed data about individual objects. These surveys weren't designed to find fast-moving objects passing through the solar system. The development of surveys like Pan-STARRS, ATLAS, and the Catalina Sky Survey changed this. These programs scan large portions of the sky repeatedly, looking for anything that moves or changes. They were designed primarily to find near-Earth asteroids, but they're equally capable of detecting interstellar objects, provided those objects are bright enough. The key phrase is bright enough. The brightness of an object as seen from Earth depends on 3 factors: its size, its distance, and its albedo, how reflective it is. Smaller objects, more distant objects, and darker objects are all harder to detect. Current surveys can reliably detect objects down to about magnitude 22, which corresponds to an object about 100 meters across at a distance of 1 astronomical unit from Earth, assuming typical asteroid reflectivity. Objects smaller than this, or more distant, or darker, would be missed. Given these detection limits, astronomers have been working to estimate how many interstellar objects actually pass through the solar system. The calculations are complex, involving assumptions about the size distribution of interstellar objects, their average velocity, and the volume of space our surveys can effectively monitor. Current estimates suggest that at any given time, there might be one or more interstellar objects within the orbit of Neptune. Most of these would be too small or too faint to detect with current technology. The few we do detect represent the tip of the iceberg, the largest, brightest, or closest examples of a much larger population. Some models suggest that interstellar objects might outnumber long-period comets in the outer solar system. If true, interstellar space isn't as empty as we might imagine. There could be trillions upon trillions of rogue objects drifting between the stars, ejected from their home systems or never incorporated into a planetary system in the first place. The detection rate is expected to increase dramatically over the next decade with the completion of new observatories. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct a legacy survey of space and time, or LSST. This survey will scan the entire visible sky every few nights, going much deeper than current surveys. When LSST begins operations, astronomers expect to detect perhaps one interstellar object per year, possibly more. This will transform our understanding from studying rare, individual examples to having a statistical population we can analyze. Imagine having hundreds of interstellar objects to study. We could classify them into categories. We could look for patterns based on their chemistry, size, or trajectories. We could start to map out where they're coming from, potentially identifying regions of the galaxy that produce more of these objects. This isn't science fiction. This is the next decade of astronomy. And it means that the pioneering phase of interstellar object science, the phase we're in right now with just 3 confirmed detections, will soon give way to a more mature field with robust statistics and deep understanding. Why do astronomers care so much about these objects? What makes interstellar visitors scientifically valuable beyond the sheer novelty of something from another star system? The answer lies in what they can teach us about planet formation, not just in our solar system, but throughout the galaxy. When our solar system formed 4.6 billion years ago, it began as a vast cloud of gas and dust, a protoplanetary disk surrounding the young sun. Over millions of years, dust particles collided and stuck together, forming larger and larger objects. Eventually, these grew into asteroids, comets, and planets. But this process was messy and inefficient. Many of the objects that formed were either ejected from the solar system through gravitational interactions with the giant planets, or never got incorporated into planets in the first place. These ejected objects became interstellar wanderers, just like the objects we're now detecting passing through our system. Every planetary system goes through a similar process. Stars form with protoplanetary disks, planets form in those disks. And in the chaotic early history of those systems, countless objects are flung out into interstellar space. This means that every interstellar object we detect is a sample from another planetary system. By studying these objects, their composition, structure, and physical properties, we're learning about the conditions in those distant systems. For example, the composition of Dwight Borisov told us that the chemistry of comet formation in that system was similar to the chemistry in our solar system. This suggests that the fundamental processes of planet and comet formation might be universal, at least within certain types of stellar environments. If we found an interstellar object with a radically different composition, say, one rich in elements that are rare in our solar system, it would tell us that some planetary systems form under very different conditions than ours. This would inform our understanding of the diversity of planetary systems in the galaxy. Interstellar objects can also tell us about galactic chemical evolution. The abundances of different elements in the galaxy have changed over time, as successive generations of stars have fused lighter elements into heavier ones. Objects that formed billions of years ago in different parts of the galaxy might have different chemical signatures than objects forming today. There's even a hypothesis, highly speculated but scientifically interesting, that interstellar objects might have played a role in the origin of life on Earth. This idea, called panspermia, suggests that organic molecules or even microbial life might be transferred between planetary systems via comets and asteroids. Now, I want to be very clear. There is currently no evidence that this has happened. No interstellar object we've detected has shown any signs of biological material. That the hypothesis is scientifically legitimate in the sense that it makes testable predictions and doesn't require any physics or chemistry we know to be impossible. If future missions could sample an interstellar object directly, imagine a spacecraft rendezvousing with one and collecting material from its surface. Finding complex organic molecules would be extraordinarily significant. It would suggest that the building blocks of life might be common throughout the galaxy, not unique to Earth. Beyond the specific scientific questions, interstellar objects remind us of our cosmic context. We're not isolated. Our solar system exists within a galaxy containing hundreds of billions of stars, many of which have their own planetary systems. Material from those systems passes through ours, and material from our system is undoubtedly passing through theirs. We are part of a galactic ecosystem, connected to the rest of the Milky Way in ways we're only beginning to understand. Every interstellar object is a messenger carrying information about that larger context. There's often a disconnect between what scientists find exciting about a discovery and what captures the public imagination. This disconnect was particularly evident with Oumuamua, and it's worth examining why. When Oumuamua was discovered, astronomers were thrilled because it was the first confirmed interstellar object, proof that such objects exist and could be detected. The scientific value was in the data, the trajectory, the spectrum, the rotation, the unusual shape. Every measurement was a piece of a puzzle that would help us understand these objects, but for much of the public, the excitement wasn't about the scientific data. It was about the possibility, however remote, that the object might be artificial, might be alien. And when a few scientists entertained this possibility publicly, it dominated the media coverage. This created a challenge for the broader scientific community. How do you communicate that the artificial hypothesis is technically possible, but extremely unlikely without seeming to dismiss it out of hand? How do you convey that the natural explanations, while requiring unusual conditions, are far more plausible than invoking alien technology? Science thrives on uncertainty and the careful weighing of evidence. The public communication often demands simpler narratives. Is it alien or not? Will the asteroid hit Earth or not? People want definitive answers, and they want them quickly. The reality is that science doesn't always work that way. Often, the honest answer is we don't know yet, but here's what we're doing to find out. And sometimes, the answer remains we don't know even after extensive study. With 3i Atlas, the scientific community seems to have learned from the Oumuamua experience. The communication has been more measured. The focus has been on them. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. Science, the trajectory, the composition, the observational campaign, rather than speculating about unusual possibilities. This is partly because 3i Atlas itself is less unusual than Oumuamua. It behaves like a comet. Its trajectory makes sense. There's no mysterious acceleration to explain. But it's also because scientists and science communicators have become more thoughtful about how they discuss these objects publicly. There's a responsibility that comes with science communication, particularly in era social media, where misinformation can spread rapidly. When a scientist makes an offhand comment about an unusual possibility, that comment can be amplified, decontextualized, and spread as if it were the scientific consensus. This doesn't mean scientists should refuse to discuss unusual hypotheses. Science advances by considering possibilities, even unlikely ones. But there's a difference between discussing a hypothesis within the scientific community, where everyone understands the context and the standards of evidence, and presenting that hypothesis to the public in a way that might be misunderstood. For content creators, and I include myself in this category, there's a similar responsibility. It's easy to get views and engagement by sensationalizing a topic, by emphasizing the most dramatic or controversial aspects. But doing so can mislead audiences and contribute to public misconception about how science actually works. This video is long, 90 minutes, because the topic deserves a thorough, nuanced treatment. It would be easier to make a 10-minute video focused just on the impact question, using dramatic music and alarming graphics to maximize engagement. But that wouldn't serve you, the viewer, well. It wouldn't give you an accurate understanding of 3i Atlas, interstellar objects, or planetary science. The goal here is to respect your intelligence and your time by providing a comprehensive, evidence-based analysis, to show you not just what we know, but how we know it. To give you the tools to evaluate future claims about astronomical objects yourself, rather than relying on sensationalized headlines. Because this won't be the last interstellar object detected, there will be others. And when the 4th, 5th, and 10th interstellar objects are found, there will again be questions about what they are, where they came from, and whether they pose any threat. If this video has given you a framework for thinking about those future discoveries and understanding of how orbits work, how we calculate trajectories, how we assess risk, and why scientists get excited about these objects for reasons that have nothing to do with aliens or apocalyptic impacts, then it will have achieved its purpose. We've covered a tremendous amount of material over the past hour and a half. We've discussed orbital mechanics, planetary defense, the history of interstellar object discoveries, and the broader scientific context. But let us return to the question that brought many of you here. Could 3I Atlas impact Earth? The answer, based on extensive observations from multiple telescopes, precise trajectory calculations using well-established physics, and analysis by professional astronomers around the world, is definitively no. 3I Atlas will pass Earth at a distance of approximately 273 million kilometers in October 2025. This is nearly twice the distance between Earth and the Sun. The object's trajectory is well constrained, with uncertainties far smaller than the actual distance of closest approach. There is zero probability of impact. The social media speculation and concern about a potential impact were based on misunderstandings about how orbital calculations work and misinterpretations of early uncertainty in the trajectory. These concerns were never supported by the scientific evidence. I've spent this entire video walking through the evidence because I think it's important that you do and just take my word for it or NASA's word, or any authority's word. I want you to understand the basis for the conclusion. The physics is sound. The mathematics is straightforward. The observations are extensive. The conclusion is certain. But while the answer to the title question is simple, the story of 3I Atlas is rich and multifaceted. This object represents the leading edge of a new era in astronomy, where interstellar visitors transition from being extraordinary rarities to being objects we can study systematically and learn from routinely. The observational campaign for 3I Atlas continues. As I record this, telescopes around the world are still gathering data, and that work will continue for several more months until the object becomes too faint to observe effectively. We can expect numerous scientific papers to be published over the next year analyzing different aspects of 3I Atlas. Papers on its composition based on spectroscopy. Papers on its nucleus size and rotation based on brightness variations. Papers on its outgassing rate and the composition of its coma. Papers comparing it to other interstellar objects and to solar system comets. Each of these papers will add another piece to our understanding, not just of 3I Atlas specifically, but of interstellar objects as a class. With 3 confirmed examples to compare, patterns will start to emerge. We lines begin to understand which characteristics are common to all interstellar objects and which are unique to individual objects. The trajectory of 3I Atlas will continue to be monitored as well. Even though we know with certainty that it won't impact Earth, tracking its motion through the solar system provides valuable data for refining our models of orbital mechanics and understanding the subtle forces, radiation, pressure, outgassing, gravitational perturbations that affect small bodies. There are also questions that will likely remain unanswered. We may never know the specific star system where 3I Atlas originated. We may never understand exactly what processes led to its ejection into interstellar space. We may never know how long it's been wandering the galaxy. These uncertainties are not failures of science, they're acknowledgments of the limitations we face when studying objects millions of kilometers away, objects we can only observe briefly before they disappear forever. Science doesn't claim to answer every question. It seeks to answer the questions that are answerable with available methods and evidence. Throughout this video, I've tried to emphasize the methodology of science, how we know what we know, why we're confident in certain conclusions, and where uncertainty remains. This methodology is applicable far beyond astronomy. Whether you're evaluating a claim about health, politics, technology, or any other topic, the same principles apply. What's the evidence? How good is that evidence? What are the alternative explanations? What do experts who have studied the topic in depth actually say, as opposed to what gets amplified on social media? In an era of information overload, where anyone can publish anything and algorithmic amplification often favors engagement over accuracy, these critical thinking skills are more important than ever. The story of 3i Atlas is a case study in how science works when it's working well. A discovery is made, observations are collected, calculations are performed, results are shared openly. The scientific community reviews and verifies the work, and ultimately, we arrive at reliable conclusions, even if those conclusions are less dramatic than the initial speculation suggested. This is how humanity has made progress in understanding the universe, not through revelation or authority, but through careful observation, rigorous analysis, and honest acknowledgement of what we do and don't know. If you take one thing from this video, I hope it's an appreciation for this process and a commitment to applying its principles in your own evaluation of claims and evidence. 3i Atlas is not a threat, it's an opportunity. An opportunity to learn about other planetary systems, about the processes that eject objects into interstellar space, about the galactic context in which our solar system exists. As I mentioned earlier, the next interstellar object could be detected tomorrow, or next month, or next year, and when it is, I hope you'll bring the understanding you've gained from this video to that discovery. You'll know what questions to ask, you'll know how astronomers will approach studying it, and you'll be able to separate scientific reality from sensationalized speculation. If this video has been valuable to you, I encourage you to subscribe to this channel for future evidence-based analyses of space mysteries and astronomical phenomena. Leave a comment below sharing your thoughts or questions. I do read them, and your engagement helps determine what topics I cover in future videos. I also want to acknowledge the sources that made this video possible. The scientific papers published about Oumuamua, Borisov, and the preliminary work on 3i Atlas. The public communications from NASA's Planetary Defense Coordination Office. The educational resources provided by institutions around the world who work to make astronomy accessible to everyone. Science is a collective endeavor, built on the work of thousands of individuals, and I'm grateful to be able to share their discoveries with you. Thank you for watching. Thank you for your patience with a video in an era of 30-second attention spans. Your willingness to engage deeply with complex topics gives me hope that scientific literacy and critical thinking remain valued in our society. The universe is vast, ancient, and filled with wonders. 3i Atlas is just one of those wonders, passing through our corner of the galaxy for a brief moment before continuing its eternal journey. But in that brief moment, it has taught us something about ourselves, our solar system, and our place in the cosmos. And that is worth 90 minutes of anyone's time. Until next time, keep looking up, keep asking questions, and keep demanding evidence. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data.